Hello everyone, this is a programming practice session for model selections. Okay. In this session, we're gonna practice a model selection example, especially using fourth stepwise selection and for the problem of the logistic regression and for the evaluation of the model, we're gonna use cross-validation. So those combinations, as the model selection method, we're gonna use a fourth stepwise selection, and as a model itself, we're gonna use a logistic regression, and for the model evaluation, we're gonna use cross-validation. So we're gonna practice these three combinations in this setting. If you, record the previous week, the programming example of the previous week, at the end we got such a plot. So if we record it, the bar actually shows the the prediction errors, and this dark one is a training error, and light one, this light one is a test error. So here we're gonna focus on this logistic regression part. If you compare with the simple logistic regression with only one the variable and multivariate logistic regression with the four variables, which use the all data, available data, then you can easily see in the training set they have the very low training error. However, test error is actually increased. It is because that this the full model is actually overfitting. So the best model, but this the simple model using only one single variable is too much simple. That's why they have the high training, and I don't know. So whether you can say this is low, but it seems to be it's a bit high. Anyway, so it is the both high error rate in the both of training and test data set. So that means it might be underfit the data. So the best, so optimal model should be between this the very simple one and this full model. So somewhere something in the middle. Okay, then the question is how can we select those optimal model? Okay, so we're gonna practice that part in this programming practice session. Okay, so in order to do that, let's move to the R programming part. Okay, here. Okay, so in this setting, so we're gonna use okay, so this is a script for in this week. Here we're gonna use the same data set with the previous one. Okay, so that's why we're gonna use this one. AMOOC 2_04 dataset iris dataset that you used in the previous week. Okay, so then similarly, we're gonna select the training index with the first 60% of the data. Then that's why we build in this way we build the data train as the first 60 samples in total. So if you record the previous week, so this data has 100 samples. Okay, so among 100 samples, we use the first 60% as a training set, and the rest of the 40% is a test. So this is okay. So let's test. Let's run this the reading data part. You can copy and paste. You can copy this code and paste on the console, but also you can just press run. Okay, this is perform the same actions. Okay. Then if we the verify, so the training data set has a 60 sample and test has a 40 samples. And if we see what kind of variables training set, then we have the four data, five variables. So sepal length and sepal width and petal length and petal width and species. So again, our goal is to find out the right classification for this species based on these the four variables. All right. But if you recall, record the how we can apply the logistic regression and get the predicted data. And okay, so this is the source code, programming code of the previous week. So this is a model. Okay, this is a model. This is the functions that can apply this logistic regression models. Okay, then 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 this comment please record the previous week. So this is the prediction using this fitted model and using the new data. However, again, this prediction just returns just the probability. So we have to assign the actual class according to that probability. That part is this code. Okay, we first predict, then using the by checking whether y is less than or the larger than this 0.5. If it's larger than 0.5, its value is true. And if this value is true, then we're gonna encode this data as the class of the Virginica. If it's a false, then we encode it as the birch color. So in this way, we can actually find out the class of the predicted y. So this is the basic stuff. However, this is the one the logistic regression. But if you recall the model selection part, we have to repeat this the model selection again and again. So at every step, so the writing of this let's say the 10 lines of the code, that's very inefficient. So that's why we actually make this process as a function. Then by just call this function repeatedly, then we can actually do this logistic regression at once. So that function is, so for you, I already make this function here. Okay, this is a function. So function name is my.lr logistic regression. Okay, then this is the function. So by saying specifying this is a function using this the function keyword, then it has the 3 arguments: formula, data, new data. This data is a training set, and this new data is a test set. And this formula is, as you know, the formula like this, something like this. This one. We're gonna regress species with petal width. Okay, so this type of formula gonna be the first argument. So the content of this function is just like what you have done in the previous week. So we first fit the data using according to this formula and using logistic regression model here, and using the given data. This is the training data that is given as the argument. Then that's a fitted model is F. Then here, using the new data, okay, here is a typo here. Okay, so this is the not typo. I'm sorry. So, okay, so because we want to predict training data set, so that's why we put the training data as a new data in the predict function. Then we predict y, and using this the factor encoding statement, we find out the predicted class of the training set. Similarly, we predict using new data. This is the test data, and similarly, we encode the predicted y using the birch color or the Virginica class. Then we finally get the y test class. So y train and y test both are the predicted class of the training set and the test set using the fitted logistic regression model. Then this data and new data both has the true class. Then by comparing with the predicted class and true class, then we can measure the error rates. Okay, so this is this comment. So error.train is training error, which is the mean of by counting and taking average of by counting the train error is not equal to the true one, the data species. Okay. Similarly, we can measure the test error. Then this return function is actually specified in the return value of this function. So what is returned is the list type of the data. So in the list data, so you can think this list is a kind of the meta structure data structure. So within in this data type, it has a field of f, and that field f's value is f, and field of it this data type has the field y.train, then its value is given as y.train. We already calculated here. So in this way, we can actually merge different types of data as the metadata type. Then we can return it at once. Okay, so we can define this function in this way. Then let's input this data. Okay, so let's see how we can use this data. So for example, if we make f is, let's say, my r, then species, then our model is we're going to regress species with petal width, then our train data is the data train, and test data is data test. Okay, then it's done. Then if we see the app, okay, so if we see the app, first the app of so the field app and $app, that is a model as a which is the output of the logistic regression function. Then f dollar y train, this is predicted class of the training set, and y test, this is the predicted class of the test set, and here is training error and test error. So if we say something like using this dollar mark and let's say error train, then we just can have the one single number for this field. Okay, this is how we can use it. Alright, so once we have this function, then next thing is we have to implement the cross validation part. Here we're gonna use the cross validation of, especially we're gonna use the LOOCV, leave on out cross validation. So if you recall the leave on out cross validation, we take one sample, then using it as a pseudo test set. Okay, then except that one sample, the other samples are pseudo training set. But importantly, this cross validation should be within the training set. Then how we can implement it. So that means we have to run this function, something like this one. So for example, this is our model, species and the petal width, and our training set is, okay, let's start from the pseudo test set. Our pseudo test set is first sample of the training set. So by taking, let's say, for example, data.train1, we can select just the first sample. Okay, this is our training set. And as our test set, pseudo test set, okay, so this is our pseudo test set. And to make our pseudo training set, all other training samples except this one, that can be done by obtained by putting minus. So what is the minus index in R, which is the all other rows except this one. Okay, then the 79 one. No, 59 one. Okay, again, if we check it, it's dimension, then it has the 59 rows. Okay, so this is the one fitting of the leave on out cross validation. However, we have to repeat it 60 times, right? So that's why instead of listing all of them, we have to make a certain program or making for loop in order to do that. Because that part is to be done so many times, so we're gonna make it as the functions. Okay, so here this is the function. This part is the LOOCV functions. So the function name is my LOOCV. And importantly, this function has the three arguments: y index, x index, and data. The reason that I use such a function is because this part, this is the formula part, because we're gonna evaluate the several models. Okay, but in this case, we have to change the actually input variables. Okay, then how so whenever you're using the different input variables, then then this the cross validation function can handle those the various inputs. So that's why I put the variable index of the y variable and index of the x variables, and in this data set. So then how can you make it from this index? Then from this index, how can you make it as a formula? So that magic part is actually here. Oh, excuse me. Sorry. So first, Cn. Cn is the column name of the data. So okay, so let's think about the data is data.train. Okay, and let's can consider y index is because in data.train. Okay, so then Cn. Okay, so let's get one by one. Let's this Cn. Cn is the cut. Oops, sorry. Then this Cn is the column name of the data. So first column name is sepal length and sepal width, petal length, petal width, and finally we have a species. So the y index should be okay. This was species. Then x index, let's say in this case 1 and 2. Okay, 1 and 2 is the sepal length and sepal width is let's say this is x we're gonna want to use. So first we're gonna make our formula as a string. So here we're gonna use the paste function. In the paste function, so if we apply the paste function, if we put the paste and the collapse is plus, then this paste function actually collapse all of the input strings as the one string by connected by this the collapse character. So in this case, Cn IXIDX is sepal length and sepal width. Then this paste connects these two strings as one by connecting this using this collapse. So if we run this one, oops, same mistake. Okay, R1 is okay sepal length plus sepal width. All right. Then we can actually connect this string 1 with the output variable indexed by yidx. And here this separation mark. Separation mark. This in this case this paste actually connect first argument and second argument with this the separation mark. So if we run this one, then str2 looks like this. Species tilde sepal length plus sepal width. So it is just string format of the formula. However, this is a string. It's not formula. So we have to change it as a formula type. That formula type can be done as a formula. So as a formula, then if we put a string as an input, then it actually changes to the actual formula type. Okay. Then you run it. All right. So we have a formula that according to this inputted y index and x index. Then here we prepare the y hat in the error vector. This y hat is encoded like this because we want to set this y hat gonna be the vector variable with the label of Verticolor and Virginica. But we don't know what's the actual predicted value of this y yet. That's why we initially make it as a true for all values. And this is an error mark. This is error vector to store whether each the cross validation result gonna be the true or not. Okay. So this is the actual the cross validation part. So by repeating from first sample to the to the last sample, we actually perform the ribbon out cross validation for each sample, right? By taking the one sample indexed by I and by using the all other sample as a minus I, then using this formula, we fit the data. That's a F. And from here, we use the predicted value. That's the F y test, F dollar y test, and this value is stored at the y hat vector variable. And also, we check the test error because we already know the true response. Then the error rate. So this error is a 1 or 0. It is technically 1 or 0 because it is a correct one, then the error should be 0. If it's the wrong one, then the error should be 1 because we only taking one sample in this case. So it is stored at ERR vector at the ith location. And finally, all of them, formula and the YCV. This is the cross validation prediction result, and error CV. This is the cross validation error. So it is returned. Okay, so let's copy and paste this function. All right, then let's try. Okay, so let's try. F.cv is my ribbon out cross validation. Then technically the output variable is the fifth one. Then here we use the first and third one as input. Then here data train. This is our train data set. Okay, so let's perform the cross validation here. All right, it's done. Then let's see what's actually, let's see y cv at y.cv. Then this is the predicted outcome from the cross validation, and the error rate. CV is the error code. So 0 means it's a correct prediction, and 1 is the wrong prediction. Then if we want to know what is the mean average, mean error rate, then CV dot err.cv. Then the error rate is 21.6 something like percent. Okay. So definitely we can actually apply this model using the actual test dataset using this MyRR. So here our formula is C.V at formula, which is like this: space is sepal length plus petal length. So we just input it as the formula in my LR function. Then we using the data and data test. Then we can check it. We run it. So in the train dataset, it is like this. Using this same model, and test dataset, test error is like this. Okay, so this is what we have done. Okay, so this is for the ribbon out cross validation part. Okay, so up to now we make the function for the ribbon out cross validation. Okay, so then next step is using this cross validation is for the model evaluation. And using this the model evaluation function, here we're gonna select models, especially use for stepwise selection. Okay, so if you record the fourth stepwise selection, so we start from the null model. Okay? Then we adding the one by one, adding the best the variables one by one. Okay, in order to make it, here we make the best model. So on the slide on the lecture note, there is a certain algorithm or pseudo code is already provided. We just implemented this the broad stepwise selection using R. Okay, so first we select we make this the best model as a null and also the error CB as a null and xi the index set. This is the full index set for for all of the available variables. That available variables are from variable 1 to 4 as an index. So we repeat it the 4 times because we have the 4 available variables. So by indexed by k, we repeat it from 1 to the length of this is the xidx set. Okay. Then first of all, because in each loop we have to to examine all available models, and among them we have to select the best one. So that means we have to store errors temporarily. That error gonna be stored in temp.edr err. Okay, so finally here, this is the actual part. We're gonna add the index in x index set one by one. So here, okay, so within this loop, x index that is actually the index that will be used in a model. That is the we put upon the best model up to now. Then we put the I. Okay, that is the current model we want to test it. So this is so using this the my LOCV, then x index. This is the current model we want to test. Then there's that string. Then using this in the 3 argument, we learn so one leave on our cross validation. Then here temp error. Temp error is just attaching the cross validation errors one by one. So here let's test it just once. So let's run it. Then let's think about k is 1. So the first one. Then let's think about how can I say that? Let's just run this code. So at this setting, so the best there's no best model. So this is we just select the best single variable, single one variable, okay, from the null model. Okay, then we run it. All right. So here temp error is looks like this. So the first error is the case that we use the first x that is the separate because if we look at the Cn, this is the x1, this is the x2, x3, and x4. Okay, so if we use the x1, in this case, cross-validation error is 40%. If we only use the separate width, we have 50%, and petal length case we have this one, and petal width we have this one. Okay, so this is when we use the one single variable. This we examine what is the cross-validation errors. And definitely in this case, best model is this one, third one, petal length. Then then we're gonna select this one as our best model using one single value. Then how can we select it? So here we can use which mean. Which mean is the returns index that actually has the minimum value among these across these vectors. Okay. Then also mean is also return the minimum value among these of this vector. So using this which mean and mean, we can select, we can update the best model. Okay, this is the best model. So best model, we attach best model. Which one? The among this x index set, that actually makes the minimum one. Okay, then error CV. Then we update the error CV by attaching the minimum error. Then we also update the x index set because if something is already included in the best model, we have to remove it. Then with the leftovers, we're gonna repeat this one again and again. Okay, so that is the broad stepwise selection. So okay, so then let's run it everything. Then if you wait a little bit second, okay, it's done. It's done. And let's see what is our best model here. best model is like this. Okay, so if we want to use only one single value, that is 3. Then, if we want to use the two variables, then it should be x3 and x4. Three variables, x3, x4, x2. And if we use all variables, that's a full model. Okay, so that is the forward step-by selection sequence, and the error and the cross validation error of this of the each model is looks like this. When you use the one single one, it has this number, this percentage of the error. When you use two, we have the lower one, and when you have three variables, it has the same but even lower. But if we use the full model, it is increased again. Okay, it shows something like in the U-shaped curve. Okay, that is expected. Okay, so here this is the cross validation. So here we're gonna use the actual training and test error. So when we use the such models, so this is a code to calculate the training and test set. So you can easily understand this code if you understand what you have done up to now. Then we finally have the error train, error test, error train, error test, and error cross validation error. Okay, so let's summarize it and display as visually using bar plot. Okay, it is like that. So this bar plot, y-axis shows the error rate, and first three bars are the model when you use one best model. This is okay here. Let's display CN again. Only this, and our best model is okay. When you only use this one, third one, petal length. This is on when you use only petal length, and this one. This one is using two variables, which is petal length and petal width. And this is the model with three values, that petal length, petal width, and sepal width. And this is about the full model case. And each of the three bar shows the error of the training set, okay, and the cross validation, and light one is the test set, actual test set. Okay, here, if you look at the training data, training error, by using the more complex or the more variables, that training error is getting reduced. Okay. However, this cross validation error is initially it is high, but getting lower, and high again. And this one, this test error is high but low, and high getting higher and higher, U-shaped curve. And here in this example, you can see cross validation error and the test error shows expected in the U-shaped curve. And there the optimal point can be found by this cross validation. Here in this case, you may want to choose this point or this point from the cross validation error because they have the same cross validation error rate on the minimum. However, by using 2 and 3, which one is better? You may want to use 3, but you may want to use the 2 variables. Okay, so either way is fine. But in conventionally, people like to use this one, simpler models. If the simpler and the complex model provide the same predicted value, same the performance in the cross validation, because the main reason is overfitting is always a problem. So in order to prevent overfitting, so people like to use a simpler model if their performance is similar or same. So that's why we want to choose this one. Okay, then here maybe it's lucky, but we have the very small test error, actual test error, as you show here. All right, so this is the everything of the model selection part. Okay, so I'm gonna stop here, and thank you very much. Thank you.